Okay, great. Okay. Hello, Sky, and what's your name, my friend? Oh, no, nice to meet you. Thanks for coming for the recitation, not recitation, Bootcamp 3 for homework 3. This is going to be about RNNs, GRUs, CTC, and you'll be taught what CTC is in the next lectures, but we'll go through each of the topics anyway. And this will be led by me, Ron, Mani, Felix, who's online, and Sid's online as well. First things first, the logistics. The homework is out, so you can download it and see it's about from Autolab. It should be on Piazza. I'm not sure about the post number, but if you can't find me, let us know. Find it, let us know. The early deadline is March 20th, and on time, like the final submission is March 27th. I don't think we expect you to work through the spring break, but if you want to, you could. And yeah, just a reminder that homework part ones don't have late days. So start working on it as soon as you can. And 3 is also a little bit more complex and a bit more work than 1 and 2. So if you start early, it just helps. A brief overview. Uh, we'll work on RNNs in 3P1. You'll implement your own RNN cell, and then you'll both forward, backward prop. I'll talk about that a bit. And then the classifier, and then you'll move on to GRUs, and then some sort of decoding methods. And the last part gets a little tricky, but I think it's really rewarding. You learn a lot. On your right, you'll see the folder structure, just like homework 1P1 and 2P1 is kind of the same, but everything's pretty self-explanatory. I think you have an MCQ notebook here, I mean a script, which essentially like you have to answer a few basic questions from the write-up. It's just to make sure you're reading the write-up. Felix, did you have a question or something? Okay, I'm going to assume no. And for the environment, you can use the same environment as for 1P1 and 2P1. Shouldn't be anything new. That's why we don't have the requirements file here. Okay, so the first thing's RNN. I think last week you have been like talked about RNN a lot. And if you came to the recitation yesterday, I talked about it too. But I don't think you were there, Juan, were you? I don't like you that much, David. I'm kidding. You're the best, bro. Um, so yeah, this is the RNN. You know about the hidden layers, which acts like memories, and then the looping figure. I think the Prof talked about it. I see it as a sushi roll or a burrito roll. You can unfold it, and that's what you get. And you don't just have one RNN layer, you have multiple RNNs. And in this homework, you'll essentially implement the RNN cell and the whole network structure eventually. Um, this is the affine function of how the output of the RNN cell is calculated. You have a hidden input that adds onto your actual input, and you have different weights for both inputs, and then you can propagate that. Yeah, the implementation is pretty similar to linear. In 1P1, you just have additional terms. And we're using the tanh function here. Sky, if you can hear me, do you want to help me out? Why are we using tanh over here instead of anything else? Any ideas?
I think the lecture says something about 10H has the best performance.
Yeah,
Mm.
you're right. But yeah, performance is a very safe word. That's a very smart play. Yeah. But I think tanh has like the least amount of gradient vanishing problem. Like it stays for the longest time for the longest number of layers compared to others. Even though that's not like very helpful, which is why once you implement RNN, you'll move on to implementing GRUs and stuff like that, which has better memory. Um, but yeah, we'll be using RNNs for phenome classification, which is a many input to one output kind of a task. And then, yeah, just like what I said, you'll implement the RNN cell and then you'll instantiate it multiple times. You will have multiple layers, and then you'll have one final um, feed forward or fully connected layer at the end, which will help you get your output. And then you'll implement both forward and backward uh, part of the RNN. I think Felix is going to talk about the next like update on RNN, which is GRUs. Felix, you want to take over?
Yeah, okay, thank you.
Yeah.
So in GRUs,
Oh, before we go
which
ahead, do you
is,
want me to continue sharing my screen or do you
yeah,
want
you
me
can
to?
continue and just share the slides. That's fine.
Oh, okay, okay. I'll just.
No, cool. Okay. For this GRU part, which is somehow one of the largest part of this assignment, you'll be implementing the gated recurrence units, and their main solution is to determine how much of previous hidden state information will be used in the current candidate state. Can you go to another slide? Yeah, you can see that we have two two gates, reset gate and update gate. Then we have the memory content, which is the current the candidate state. And the memory state depends on the reset gate. You can see that the reset gate will determine how much of the previous information we'll use in this candidate. And if it is set to 0, this layer becomes a simple RNN unity, as we've seen from the previous slides. And the update gate will determine how much of the output of the state that we will use. As you can see, the previous information is scaled by the ZT factor, which means that if it's 0, this the second part of this function will be 0. And 1 minus ZT determines on how much of the memory content that we consume in the prediction of the output of this time step. So this means that that's why we use a sigmoid function. Could you go to another slide? Yeah, the reason why we use the sigmoid function in the reset gates is that it has a value between 0 to 1. You can consider it as a probability, as you can see from the when we are trying to determine the hidden state information, we are we are using the probability of 1 to determine the memory content and the previous hidden state information to use. Next, right? Yeah, so in this, you can see that you have two distinct operators. The one in blue is the Hadamard product, which is element-wise product, means that we are expecting these values to be of the same shapes. And the dot product is a normal standard matrix multiplication operation where you can use the NumPy matmul. Yeah, so as I've said above, we are using the element-wise product with linear transformation of the hidden state, and then we combine that transformation to the candidate information we've stored to determine the current hidden state predictions. The next slide. Yeah, so as I've said, this is the longest question in this homework, and all intermediate gradients of weights and biases should be correct to make sure that your actual gradients of the inputs are correct, because you will find that we have so many operations means that we will have many intermediate gradients, and when you're doing the backward propagation you have to be careful, otherwise you might implement the forward pass correctly but the backward will fail for some reason. So you have to be careful when you are implementing these operations. We have provided some resources on how to compute the derivatives, and the best approach to this problem is to try to break down this function into some decomposable simple operations so that you can trace your gradients backward easily. If you stack all operations together, it will be super hard to implement the backward the backward passes of the operations that you've performed. Yeah, so the one other thing to consider is that it is pretty straightforward that the reset, update, and memory state and the hidden state, all of them have the same shape. So you have to consider that during your debugging. And the bias or parameters all have the shape of hidden size according to the layer that you are on. And during the addition, they implicitly broadcast to the batch size. So it's when we are doing the element-wise addition, the batch size, the bias parameters will be broadcasted to match the shapes of this hidden state information. So you have to be careful with the order of operations. As it becomes trickier, the more you have many operations. Yeah. So this slide goes through how you compute element-wise multiplication and the backward pass. You can consider this as like a simple derivative calculation when you have, let's say it's like a single variable calculations, but for many elements. So that's what you should consider. It's simple and pretty straightforward here. Yeah. So the character predictor that we have here is different from the one we had for RNN. As for RNN, we were considering it was a phoneme predictor, and we were considering only the last hidden state. But for this problem, we will be predicting at every time step. So the ones that we'll be implementing is this many, too many, not the delayed sequence to sequence, which is the first figure. And you will be predicting the characters from the input time steps. So once you implement your GRU, you will use it to implement some inference character predictor. Yeah, I think that was it for GRU. Any questions?
Hey guys, I hope I'm audible. I'm sorry, I'm on the in the airport lounge right now, but I try to do my best with CTC. So, would somebody be able to shuffle the slides for me?
Yeah, I got you.
Oh, thank you, man.
Yeah.
So, okay, wait, talking about CTC. So we've trained a model using the CTC loss. So that's why our RNN is now it's going to be basically splitting out a probability distribution for a vocabulary every single time step. So we're going to try to see how we exactly turn that matrix of probabilities into an actual readable word in the sentence. So that's where the decoding comes in. Um, it's basically the calculation of a loss from a target sequence. Can I have the next slide, please? Yeah. Okay. This is all. Uh, these files are basically included in your code base, and it's pretty self-intuitive. Uh, okay. Extend with a blank. So this is basically to make a sequence to have a fixed sequence. So you got to basically append your sequence just to make sure that your all the sequences going into the model are of the exact same length. So we're going to pad it with blanks after every other word to make sure that we have a single sequence. The length can be decided on your own, or it's basically given in the PDF. I would recommend people follow the recommended length which is given in the PDF so that every single sequence coming in and out going into the model is the same. Uh, I also say this because the uh, the test cases are going to be based on the same sequence. Next slide, please. Yeah. So we're also gonna skip connections there. That's true. We're also gonna skip connections because we're working with RNNs here, and you know why we use skip connections. When your model becomes too long, it's basically used as a counterweight against vanishing and exploding gradients. Next slide, please. Oh, this is the calculation of forward probabilities for CTC decoding. Uh, we basically, as we go from like a sequence to other, we calculate the forward probabilities given the posterior, given the prior x, given the prior of x. So the probability is that your next sequences occur or appear from S0 to S3, and they're equal to the to SR given your prior of x. It's basically the summation over the prediction of alpha, which is like the CTC loss. From which takes in function, which is a function of your time and q, uh, and which is then multiplied by YT SR as per the uh, uh, as per the CTC rule. Yeah, this is the dynamic probability table, which you guys would also find in the PDF. You basically have your alpha, and you give your input to form each of the sequences. As you can see, all the sequences are like padded with zeros, just to make this all the sequences of the same size. And we also use skip connections here. So this goes from t equal to 1 to the last time step, which is like t equal to 6 here. And this helps us to like calculate all our probabilities. We multiply it with our input probabilities, obviously, which is because if you see the equation, it's alpha into YT. So it's basically multiplied by your inputs for calculating the final output. That's how we calculate the loss, you guys. This is like a dynamic programming table, which you can intuitively also find on the also find in the PDF, but you can also like go through it in the ctc.py file that we have. This is the backward algorithm. This is basically when you backprop. So instead of alpha, you have a beta here, which is also a function of t and r. If you remember, alpha was a function of t and q back there. Here, similarly, beta is going to be Similarly, beta is also going to be a function of t plus 1 in q instead of t minus 1 in q in the backward algorithm, because this time you're going right to left instead of left to right, since as per the backprop algorithm. Yeah, pretty intuitive. Nothing's changed. We just backprop as in we would backprop with any other loss. Um, we end up learning beta. The posterior probability that I was talking about earlier, it represents the probability of having a state given at any time t. So having a posterior at t minus 1. Giving a prior, pardon me, at t minus 1, you update your probabilities to create a posterior at p. So your probability that ST would be equal to SR given your priors of S and X. So to update your posteriors, basically, it's alpha into beta. So it's like your forward CTC multiplied by your backward CTC, given all the summation of all your forward and backward CTCs. Yeah, this is basically called gamma, which represents a posterior probability. Again, you can find you can read more about this in the PDF, and it's quite intuitive from the code too. This is the final CTC loss computation. Once we know the posterior probability, we can actually just plug in those values to ultimately train our network, because we have calculated the loss now, which we're going to continuously update. So it's basically you've calculated a gamma, as you can see, and then we use a gamma to basically calculate a logarithmic function, which is basically the divergence multiplied. So the way we calculate this divergence is basically multiply the probability with the log of your input, basically, which is like capital Y, which is a function of the time in S. Um, as you'd see, we have like uh, it's basically two summations here. So there's an internal summation and there's an outward summation. It's because we're summing out all the time, like the complete time steps over all. So basically all the sequences at each time steps and at all states too. So we have like two summations here. Well, finally, we can directly use it to we calculate we differentiate the divergence, basically like the loss to train our network. So we have like summation of gamma with 1 by YT, which is basically common taken outside, because it's like your input at the first time step, so YT raised to 1. Next slide, please. Yeah, I think this is Mani's part.
Yeah. So I'm Mani, and I'll be talking about CTC decoding. So till now, we have a model that predicts something, and you have some data. So you train the model using CTC loss. And once you train the model, you need to serve the model to users. So while serving the model to users, I can't just give the logits to user. When you pass some input to the model will give you logits over multiple time steps, and if you give them directly to user, the user won't know what to do with it. So imagine ChatGPT giving you a bunch of numbers and asking you to figure out what it is from that. It's not a good thing. User won't be pleased with that. So we need to get the final output sequence from those logits so that the output is meaningful. So in this, we can see that we have the yellow box is the time step, and you can imagine it's a model that's predicting something at each time step. So we have 7 time steps, and for each time steps, it's predicting some probability distribution over this symbol set. Now we can't make anything out of it by seeing these numbers. I don't know what it is predicting. So we need something that decodes from these numbers and gives some meaningful output sequence. And that's what CTC decoding does, and this is why we need CTC decoding. So this process of converting these probability distribution to the output sequence is known as decoding. So in this homework, you will be implementing 2 decoding algorithms, which is beam search and greedy search. And you will be implementing both of them in the ctc decoding.py file. And in both of these, you will be writing the code in the decode function of 2 different classes. And in this picture, you can see that uh, from these logits, I'm decoding something and I'm getting some output called bat. Now, this is some meaningful output that user will understand and everyone can understand, and not these numbers. And this is what decoding is. And before we go further into CTC decoding, let's cover some basic terms, because this is not yet covered in lectures, and this will be covered in the upcoming lectures after spring break. So in the previous picture, we saw something called symbol set. So what is symbol set? You can imagine the symbol set as a set of class that model gives probability for all these class. So for each time step, model gives you a probability distribution, and these are the classes that model will give the probability distribution for. So for every time step, the model will output a distribution for all these symbols or classes. So I have given an example on the right picture. So we can see that at time step 0, the model is giving probability for each of the symbol dash A, B, C, and T. And this will add up to 1 if it's passed to softmax layer. And this is also known as vocabulary, and these 2 terms are used interchangeably, but in the write-up, we refer to this set of symbols as symbol set. And if you notice at the top of the symbol set, there's some symbol that resembles dash. So this dash is called a special symbol. So it's mainly used in speech tasks. So this dash or blank symbol means nothing. It means if the model outputs dash in that time step, or if the model output blank symbol in that time step, it means that like it nothing is emitted at that time step. Like it's like you can think of it as like there is no meaning for this particular prediction. So like this symbol is used in various cases. For example, when we have a audio transcription of someone speaking, like the person won't be speaking for the whole audio. There will be some silence at the start of the audio and at the end of the audio. And if we don't have this blank symbol, the model will be forced to predict something at those frames or at those parts of audio. So in order to avoid that, and in order to avoid forcing the model to predict something based on the probability, we use these blank symbol so that it represents nothing. And another use case is that uh, every speaker will have their own rate of speech. Someone will speak very slowly and someone will speak very fastly. And when we are processing speech transcription, we first convert them to frames and then we feed these frames to the models. And these frames are usually 25 milliseconds to 30 milliseconds long, which means they are very small and they capture only a very small portion of the audio. And this also means that as multiple frames can represent the same character or the same phenome. So here we can see that the model will output something called bat, like with multiple A's, even though the expected output is bat. So how do we even check if both are like the expected output and the model output is same. So what we do here is we collapse all the A's into single A, and this is called as compressing or collapsing, and we'll be using this throughout beam search or greedy search. So we know that if there are repeated characters, we'll collapse it. But what if the word itself has repeated characters? For example, in hello, we have two L's. And if the model predicts something like HELLLLO, we can't just collapse all the L's into single L, which will give us HELO, and that's wrong. So we need something to separate the meaningful repeating characters, and this is where dash or blank symbol comes into picture. So if the model predicts blank symbol, it means that uh, it's like a separation for multiple repeating characters. For example, in the bottom, in the last example, we can see HELLL dash, and that's followed by 2L and O. Since it's divided by dash, whatever repeating characters comes before the dash will be collapsed into a single L, and whatever comes after that blank symbol will be collapsed into a single L. And by that way, we can decode this into hello. Any questions till now? Okay. So as I said, we'll be implementing greedy search and beam search. For greedy search, as the name suggests, you just need to be greedy. For each time step, you just need to pick out the symbol that has the highest probability and then move on to the next time step. So in this picture, we can see that at time step 0, we can see the blank symbol has the highest probability. So we pick that. And when we move to time step 1, we can see the symbol B has the highest probability. Similarly, we do that for all the time steps, and we end up with something called blank symbol B, blank symbol A, A, T, and blank symbol. And once we get all these things, we need to take care of repeating characters and blank symbols. So as we discussed earlier, we need to collapse all the repeating symbols. Here, we can collapse both the A's to a single A, and we need to remove these blank symbols, and this will decode to BAT. And this is what research is. This is worth 5 points, and this is probably the most easiest part of this assignment. And next is beam search. So in greedy search, we picked the symbol with highest probability. This also means that we are very short-sighted. We don't care what occurred before and what will occur after that time step. So we are just picking something on what we are seeing right now. So we are making some decision that's short-sighted. And the other extreme is we explore all possible paths. So instead of picking the highest probability, we pick all the possible paths and we try to explore all possible paths. And this is called exhaustive search. But the problem is since we are exploring all possible paths, this will be exponential and it's not computationally feasible. So we need to strike a balance, and this is where beam search comes. So in beam search, instead of keeping one best path like we did in greedy search, so we keep multiple several paths at a time for beam search. And the number of paths that we keep at each time step is called beam width, and it's usually denoted by K. So what we do is at each time step, we have something called hypothesis. Hypothesis is nothing but the possible candidates at each time step. So we have some hypothesis at some time step, and then we extend all these hypotheses with the possible symbols, and we'll compute the score, and then we'll prune the candidate hypothesis so that we keep only top K candidates. So right now it will be confusing. I'll go through an example so that it becomes clear. And another thing is we should not forget about blank symbols and collapsing. And I'll show through example why we need to do this, especially for CTC. So let's go through vanilla beam search first. And this is not the beam search variant that you will be implementing this homework. You will be implementing CTC beam search, which is a little bit complex than this, but this will be useful for understanding what even beam search does. So here you can see initially there is nothing first, like which is an empty list, and the vocabulary is 5 A B C D E, which means that we have 5 symbols here. This is a vanilla beam search, so we don't have any blank symbols, and the beam size is 2. So at the first time step, the model predicts a probability distribution over A, B, C, D, and E. And since the beam size is 2, we'll have two hypotheses. So we pick the top two symbols with highest probabilities, which in this case is A and C. And we call these two as hypotheses, and we'll extend these two hypotheses in the next time step. So in the time step 2, the model will again predict the probability distribution over the symbol set. And what we'll do is we'll extend the hypothesis, which is A and E, with respect to the probability that the model has predicted at time step 2. So at time step 2, to calculate all the candidate sequence, what we'll do is we'll just extend the sequence. For example, right now, the candidate sequence can be AA, AB, AC, AD, AE, and the second set of candidate sequence will be CA, CB, CC, CD, and CE. So we will have 10 candidate sequence at the second time step. And since beam size is 2, I'll just prune these candidate sequence and keep only the top two sequence. Top two candidate sequence. So in this case, since we can assume that AB and CE had the highest probability, so I'll just keep those two sequence. And again, in time step 3, I'll do the same thing. The model will predict probability distribution over the symbol set, and I'll be extending the same thing. I'll be calculating probability for every possible candidates. For example, in this case, I'll be calculating ABA, ABB, ABC, etc., CC, CEA, CEB, and CE, etc. And again, I'll prune it and I'll keep only the top two sequence, which ends up with ABD and CED. And at the end, I will just pick out the one which has the highest probability. So by this way, you are keeping multiple options at each time step so that you don't lose out on options that seem less promising at the start of the decoding. So this is vanilla beam search, and CTC beam search is a little bit complex. So it becomes complex mainly because of the blank symbols, but this can be easy if it's understood properly, or it will be very hard to implement and it can get tricky sometimes as well. So in this, I'll take beam size of 3, and you can see we have a vocabulary of 3 symbols, which is blank symbol A and B, and we also have the probability of those symbols at each time step. We have 3 time steps here, and that's given in the table on the top. So going through the diagram, first we have something called start of sentence symbol, which means that nothing has been predicted, and the model is yet to predict something, and the model is predicting some probability for all the symbols in the symbol set, which is blank symbol A and B, and the model predicts 0.49, 0.03, and 0.47 for these. Since we have beam size of 3, we'll keep all these 3 probability and we'll start extending from next time step. So in time step 2, again, the model will predict probability distribution over the vocabulary, and we will extend the hypothesis from the previous time step with all possible symbols. So here we can see the blank symbol, which we predicted in the previous time step, is extended with blank A and B. Similarly, A is also extended with blank A and B, and same for B. So at this point, in vanilla beam search, we would have just picked the top 2 probability and we would have went ahead with it. But since it's CTC beam search and since blank symbol is involved here, we have to do something called collapsing. So as we discussed earlier, this blank symbol and A will collapse into a single character called A, and this AA in the second table will also collapse into A. So these two will output the same symbol after collapsing. So this is where things get complicated. So since these two collapse into a single character, we need to add these two probability and consider these two as a single output sequence. And similarly, we have dash these two blanks, which collapse into a single blank, and similarly for all others. So, and since we have a beam size of 3, we take all the top 3 probabilities. And in this case, to calculate the probability of this output symbol A, we need to add the probability of this blank symbol and A along with AA, because they both output the same character then. And again, the model will output probability distribution over the symbol set, and again we repeat the same process, and we end up with three beams, and at the end we just choose the output sequence with the highest probability. And this is a high level approach for beam search, and we went through all of these through in the example earlier. So I'll skip this for now and I'll go into the pseudocode. So for the beam search part, you can directly implement this pseudocode, which is very easy if you understand. I'll go through the pseudocode once. So what you have to do is you have to initialize two dictionary, which is active paths and temp paths. Active paths stores only the top k beams at each time step. And temp paths is to calculate all the possible candidates for each time step. For example, the active path will just, if you look at time step 1, the active path will just store blank symbol A and B, while the temp paths will store these symbols in the tables, which is blank, blank, blank A, blank B, etc. So you will make a dictionary, and what you will do is you will iterate through the probability for each time step. So let's take, if you are at time step 0, you will pick all the probabilities from that time step, and you will extend all the symbols for them. And you will try to update the score, and you will try to update the path. And most people get confused when they are computing a new path. So when you are computing a new path, there can be three scenarios. So the first scenario is when the new symbol is same as the last symbol. For example, here, when we are extending here, extending this A, and the next symbol is A, this can be collapsed. And this is the first scenario that was discussed. And the second scenario is the last symbol of the path is blank. So the second scenario is this part where the new symbol is blank. And the third scenario is the last symbol is different from the new symbol and it's not blank, which is this one, AB. And all these three things, all these three different scenarios should be handled separately so that your code works right. And you need to be very careful when you are doing these three, because most of the people get stuck at this part and the final decoding algorithm won't work solely because of this part. So once you extend your path, you need to calculate the probability for the path you made. So that's what is being done at line 8. And from line 19 to line 14, we are just updating the probability for the existing path. So I mentioned that multiple paths can collapse into a single path. So which means that I need to add the probability of the paths that collapse into the same path. And that's what is being done in the if statement. And in the else statement, what is being done is that if you encounter a new path, you just create a new item in the dictionary and you will proceed forward. So you will iterate through all the symbols, and at the end of that, you will sort the symbols based on the probability that you got at the end, and you will just keep the top k paths, and that is done in line 4. So this is the core of the algorithm, and this will do all the calculation for you. But there are some housekeeping that we need to do so that we get the final path. So this line 20 to 33 basically does housekeeping, and it selects the best path. So what we do is, so even at the end of even when we complete all the decoding till the last time step, there can be a scenario where the last symbol is blank. If it's a blank, we discuss that it represents nothing. So we need to remove all those blanks, and when we remove those blanks, that particular path can resemble to some other path which we have already calculated. So we need to merge those paths again, and that's what is being done in line 23 to 28. And from line 29 to 31, we are just getting the path which has the highest score. So this is the whole beam search pseudocode, and again, just be careful when you're handling all these three cases. Yep. So any questions with beam search? Okay. And yeah, and so let's put everything together. So Ron covered RNN, Felix covered GRU, Sid covered CTC, and I covered decoding. How do we put everything together? We have a model. We can either have RNN or GRU. So we train the model using CTC loss to avoid the alignment problem. And at the end, we'll have a model that predicts something. So it will give us a probability distribution over symbol set. So since we need to do inference on the model, we need some decoding algorithms. So we use greedy search and beam search to decode and give the final output sequence to the user. And this is all for homework 1. Any questions now? Okay. I'll hand over to homework 3 part 2 team.
The homework 3 part 2. We start with the logistic for this homework. The early submission, which is due on 20th March, 11:59 on Eastern Time. That's the cargo submission, and completing the homework 3 quiz on Canvas. And the on-time submission deadline is 27th March, 11:59. And for this homework, you don't have to, you will not use attention, so no transformers for this assignment. And the parameter limit is set to 20 million. So yeah, this assignment, it will require a lot of time. So the notebook provided with the starter code, it has many to-dos, and you have to start early so that you can complete everything early. The training, it takes some time. It's better if you use PSC or you manage to start early. Yeah, so doing the homework 1 part 2 recap, because it has some this homework 3 part 2 is somehow connected to the previous homework 1 part 2 that you finished. The homework 1 part 2 was about flame to flame classification, whereby you could take the simple word, the input could be like recording the speech with a simple word yes, and this was converted in MFCC feature vectors of 27 dimension, and this could be passed down into the model that would later on provide the final labels with this format of output. But there was some issues like redundancy. As you could see, there's some Y that is repeated and E repeated, SS kind of repeated, and this is what we referred as time synchronous, whereby each flame was having one label at that time. So yeah, yeah. To explain some issues with this homework 1 part 2, there was some redundancy of the phonemes in the output prediction provided. As you can see, this Y were repeated and this E, that's not how it's supposed to do. And this is not how normally human transcript. And it was time synchronous because there was label linked, one label linked to one flame. So it wasn't that good. So this homework 3 part 2 is here to solve that issue by using sequence to sequence mapping. And the final output is a bit clear with just yes, and is what we call order aligned, but not time synchronous. This is natural, and this is how we normally transcribe. So this is how we're going to do this in homework 3 part 2. The features are going to be the same as the one we used in previous assignment, homework 1 part 2, but the labels will be ordered by synchronous but not time synchronous. And the output should be the sequence of phonemes, which are precisely indexed and clear. So the output, it should be like clear, like this word Bhiksha, it should provide this clear output, not the output with the repeated labels or wrong output. So you will use the CTC loss. They explain it in part 1. This is provided by PyTorch, and this one is here to help you deal with the variable, different variable length. And the metrics to use for this assignment is mean, Levenshtein distance. And yeah, these were provided in starter codes. So one more thing to notice is that in homework 1 part 2, That was an equal length of input. You could easily stack everything in rectangular tensors. It was just straightforward. But for this homework 3, part 2 is way different because you have variable length sequences whereby some lengths are shorter, others are long. So there's a way to deal with it. One way to deal with it is using padding, whereby the first thing to do when you're performing this padding is to first store the unpadded length. This was provided in starter code, the variables length x and the length y. So this padded, the shorter length are padded with some zeros so that it can have the same length as the longer length. And to do that, there's some issues with the padding. As you can see down here, some lengths are very short, others are a bit long. If you just pad everything with zero, it means that when you're computing, you will waste a lot of resources, and this is not efficient with the space. That's why we go for packing the batch of variables, given that there is a list of tensors to be packed, and each element has different time steps. So the first thing to do here with the PyTorch is to first sort these tensors in descending order based on the number of time steps and in each sample, so that this one with a high number of time steps comes first and others follow like that, so that everything's sorted in descending order. So finally, we get this final 2D packed tensor, whereby at each timestamp, like zeros are selected on each element, like 0 timestamp from each sample in the list, followed by 1 like that. And at the end of the day, we have this column instead of the rectangular stack. So the packing has different functions. This pad sequence that pads the batching, takes the original list and pads everything into the length. And the padded sequence, it takes the padded batch and the sequence to sequence together and merge everything together. And later on, we perform the reverse by unpacking back to the batch of the padded sequence. And finally, we use this collect function to be able to perform the data loader argument to make sure that everything is ready before passing down to the model. Yeah, let me invite Yabsela to continue with the ACLR model setup.
Thank you. Hello, everyone. I'm Yabsra, and I'll be continuing about the automatic speech recognition model that you'll be implementing for homework 3P2. So such tasks as audio automatic speech recognition or machine translation, you oftentimes use encoder-decoder models or sequence-to-sequence models. These are specifically used where you have an input sequence of a specific kind and you want to change it to a different kind. For instance, in machine translation, you will have an input sequence in one language and you want an output sequence in a different language. In this case, you want to use a sequence by sequence model. And in our case, where you have an input sequence, which is just a vector of utterances, or like they basically represent the speech, and you want an output sequence that's basically a phenome representative. It's a sequence that represents what these are, but in text form. So again, we can classify to two sections, the encoder and the decoder. The encoder sections, the one you see over here, they'll have multiple layers. We'll go each of them. You have our input, the MCC features, and this will go through an embedding layer, which is optional. We'll go through that. Then the sequence layer, the major part. And sometimes we want to make a downsampling. Like Floyd explained, our input is going to be a 100 millisecond or 100 second utterances, but the output will be much less. So sometimes we want to downsample, and this will finally create a latent embedding and this will go through your decoder. The decoder is a basic classification. A decoder is very similar to what we did in homework 1P2, and this will go through the decoding, which they explained earlier. So let's begin with the encoder. This is typically used to generate a high-level representation of a given data, similar to what we did in homework 2. There are no labels to train the encoder. The encoder will be trained from what's left, basically what's given from the decoder, and they're trained together. It can be any network, CNN, RNN, linear layers. You sometimes often use like attention or something like that, but attention isn't allowed, as mentioned earlier in this assignment. The decoder is a network that takes feature representation and tries to generate the closest match to expected output. In homework 1, we got the raw input and passed it through the decoder. Like it's like the first homework was kind of like a decoder, but if you add an encoder, the input from the encoder, it will amplify the results of the decoder, and the loss function is applied directly to the decoder and it will be trained backward. Is that clear? Okay, so the first section of the encoder is the embedding layer. Again, like I said earlier, this is optional but highly recommended. It's oftentimes used to increase or decrease the dimensionality of the data. For instance, let's take an NLP task where you have 100K vocabulary representation, where each word will be a one-hot encoding, where deep might be the first row and neural might be the second, and so on. And you can use this, but this is a very sparse representation. But by using an embedding layer, you can decrease the embedding size. So it might give a better representation of the input, and also you can decrease the size of the input, which is very important when you're running something like an RNN or LSTM, which can get computationally very expensive. So embedding is very important. And sometimes you also want to increase the embedding where you want better feature extraction. So something greater than a 27 dimension by making the embedding larger. If you want your input to be larger, you can also use an embedding layer. We can take this example here where we have your time steps and your features. By basically running a CNNC through number of 5 filters, you're basically increasing the channel output. Your channel input would have been 3, but now your channel output can be 5. But as you did in homework 2, you can manipulate your other parameters like your padding, stride, etc. Okay, there's a class that is defined in your notebook that's called promute. This is very important. Now, as the input, as Freud mentioned, is batch size, max time length, this is after it's padded, and the number of features. But if you remember from homework 2, our input was the batch size, the channel, and then we have the length. So the feature and the features and the length has been switched. So before you call your convolutions or before you call your embedding layer, make sure you make it to pass it through the permute class. And after you're done, you're going to pass it through the permute class again so that you can go to your sequence model. So this is a very important note. Okay, so stride. Increasing your stride is also one way to downsample. As mentioned earlier, sometimes you want your dimension to be smaller than the actual input. In that case, increasing the stride will achieve the same thing. So stride 1, you'll get your same time sequence, but increasing the stride will let you to get a small time sequence that's more concentrated as well. Now, increasing the stride can help you, can improve your dimensionality, but also make training faster because less time sequence means less time training it. But increasing it too much might also create a loss of information, and we don't want that. So we don't recommend downsampling more than 4 times. And this includes both this, and then we also see later on the pyramidal BLSTM. One thing to note, like Flori mentioned, we're going to be padding and packing the sequences. For here, you're going to require your X lengths. But if you're increasing your stride for more than 1, that means your time sequence will change. So you must calculate your length X accordingly. You can use the same formula you did where you have your input length subtracted by the kernel length, summed up with 2 times of the padding divided by the stride. And you can clamp this length to basically your embedding before you call the torch function. Now, even though we've been using convolutional layers, you don't have to use convolutional layers. You can use an iteration of this as well. You might have tried residual blocks in your homework 2, P2, and you can also do that here as well. The second part is your sequence models. Your sequence models can be RNN, GRU, LSTM, and so on. This is basically what was explained by the homework 3 P1 team. We recommend LSTMs because they have longer memory storage. And also all this RNN variant, they expect padded sequences. So when you're implementing this, keep in mind on the earlier slides that talked about how to pad it and how to pack your sequence. And after the output of the LSTM, you want to unpack it as well. So this would be what the parameters of the LSTM. This will more likely be the model you're going to be using. It's going to be your input size, 27, or your embedding size that you selected. Hidden dimension, very important. The number of layers you want. Dropout, you don't want to add any dropout like you did in previous homeworks. You can just put in your rate here, bidirectional or not. One thing to note about this assignment, we're given the full sequence. So it's not like a streaming process where you have half the sequence and you use the layer of the sequence. You have the full sequence. So you can see both direction. So you can use bidirectional in this situation. One thing to note, if you're using bidirectional, you're going to get two hidden dimension. Basically, the output will be two hidden dimension because you're going to be doing forward and backward as well. So that's something to note. Okay, the last section of the encoder will be PBLSTM or bidirectional LSTM, pyramidal bidirectional PLSTM. It's the same thing. The only difference that it differs from BLSTM is that at every step, you're going to be concatenating adjacent time sequences and basically concatenating them as they are the different features. This can be easier to see. So here we have 8 time sequences, 3 features. We're going to first separate them on adjacent ones. So we first have the first 2, the latter 2, and so on. And then we're going to concatenate them. So basically, instead of the time sequence, we have feature-based. So here it was 3 and 8 time sequence. Now it's going to be 4 time sequence and 6 features. So this will be concatenated and this will be in your data. This will be fed into the BLSTM. Like I said earlier, BLSTM will have 2 times the hidden size. So even though this hidden size is 5, you're going to have 10 hidden size, both direction considered. Okay, this is what the pseudocode will look like. Again, it's the same thing. So we have your batch lengths here, right? So you're going to divide your time sequence by 2, that means deduct it by 2, and you're going to increase your feature lengths 2 times. So this will be the same, and this will be fed through the BLST, and this will be your output. This is the pseudocode for that. The next would be the decoder. Decoder is just a classification layer. It's very similar to what we did in homework 1P2. Outputs from the sequence layer goes to a classification layer. So you're going to go through all the different layers, linear layers. You can make it deeper, you can make it wider, different activations, dropout, and regularization techniques. And after that, you go to the softmax to get your probability predictions. And that's it for what the model will look like, an overview of the model. And Pranis will continue with the hyperparameter.
Cool. Hello, everybody. I'm Praneeth, and I'm going to continue from where Yapsara left off. So first, we're going to start by continuing about hyperparameters and regularization. So as you guys have already seen in your homework 1P2, right now we're dealing with this MFCC data, which is basically a lot of this voice data and speech data, right? So it's very important that this data needs to be normalized because the way we record it can be done in very different environments and a lot of randomness exists. So to ensure that all this data is normalized, we will basically subtract the mean and divide it by the standard deviation. And apart from this, it is also important that we use different weight initialization techniques. Instead of just starting with random weights, we can start with using these weight initializations like K-Ming or Xavier, especially for your convolutional and linear layers here. And this proves to be much better. And another thing is, you should actually make sure that you follow things like using of weight decay because it actually helps in preventing overfitting. And at the same time, we also need to use the proper optimizer, something like AdamW or Adam works pretty well over here. And in this homework, especially, one thing that's very important is the scheduler. So what we've noticed a lot is that reduce LR on plateau is something that's very good for homework 3P2. And the Levenstein distance might start to oscillate to lower values using this. Another scheduler that we could actually make use of is the step LR. There's also something good. And yeah, the optimizers that are pretty good right now for this homework would be AdamW and Adam. And once again, with the learning rate, as you would have observed with the previous homeworks as well, start with a small learning rate, something like 1 into 10 power minus 3, something good to start with. And then based on performance, you can see like what to do with it. And something that's very important other than this is adding dropout. So dropout layers need to be added in all of the 3 layers. We need it in the embedding layer, the sequence model, and the classification layer. And once again, through experimentation, always good to start off with the small dropout rate and then increase it as your model is getting trained. And with LSTM especially, there is something called log dropout. This is what we need to be using for our bi-LSTM and pyramidal LSTM layers. And this log dropout can actually be, the basic idea is that it can be used to apply the same dropout mask throughout every time step rather than varying it throughout the time steps. And to have a better understanding about this, you can actually go through the documentation over here from PyTorch. And yeah. And once again, since we're dealing with the frequency data, MFCC data, it's always good to do time masking and frequency masking. This is something that actually helps in generalizing your data. So your model is actually learning rather than just memorizing things. So this will just be masking a little bit of the time steps and a little bit of the frequencies. Another thing, as we discussed, Mani was talking about like the decoding part and how we use beam search, right? Beam search is actually the proven one to do the best in terms of getting better results. However, we do not want to like have a beam width too high because then the computation just becomes too much and we cannot afford that much compute. So that's why for all of our homeworks and our testing, we use a beam width of around 50. But the thing is, because for testing, it's always good to have a beam width. But when we're actually training our model and we're running epoch by epoch, we don't want to keep the beam width too high there because when we're in the validation stage with the beam width, right, it's going to be taking a lot of time to run each epoch. But in our validation stage, we just need to verify whether our model is working good and all. So it's better we could actually go with something like greedy itself there so that you can run your epochs faster, or maybe reducing your beam width to something lesser in the training stage. But finally, when you're dealing with your test data, use a higher beam width, and 50 is the ideal one, I would say, for this homework. And final tips, guys. So make sure you split the work within your study groups. This is like a much harder homework compared to the previous ones. So yeah, make sure you do it well with your team and run your applications properly. And also don't forget to attend the lab on March 14th. This is a really good lab to actually get a better understanding on CTC loss, beam search, and all these things. And it'll be very useful for your homework. So good luck to all of you guys, and thank you.